Okay, so I know I'm the last talk before dinner, so I'll keep myself short. Yes, I'm Max. I think we've all met by now, nearly all. And I want to talk about deep learning in molecular communication. So, how did we start? I don't have to explain to you what molecular communication is. We saw that deep learning in molecular communication has been applied close to not at all. So if we look at publications, there's one or two examples, a few more to be honest, where it's been used for very, very low data rates and let me call it superficially. So we wanted to look at specifically our test bed. Can we use deep learning to make our life easier now and in the future? In general, deep learning allows for some kind of classification, especially in communication problems, and has the advantage that we kind of need less analytical knowledge before we get started. Ideally, we don't actually have to know anything about our system. We can just throw it into a machine and get some kind of working model out of the other end. That's the dream that I have sometimes. In our case, we used a subform of convolutional neural network. I'll go into more detail about that later. Basically, in short form, in molecular communication, deep learning has only been used for on-off keying with effective data rates of below 2 bits per second. This is our test bed. Some of you know it. This is kind of the newest iteration. So we use superparamagnetic iron oxide nanoparticles, ions for short, or just magnetic nanoparticles to transmit information through an active background flow. So that's what you see here. We have a peristaltic pump which drives water through a tube, and we use micropumps, and the commercial ones, in this case some ones which we got from Fraunhofer, to inject these particles into our transmission tube. They travel with the background flow to a receiver where we can detect them due to their magnetic properties. In this case with an inductive sensor, so when the magnetic particles are inside the inductor, the inductance value of that coil changes, which we can detect with some halfway complicated circuit. This is our sensor signal at the end, so here's just some kind of transmission samples for 1 symbol per second, 2 symbols, 4 symbols, at different injected volumes, so ranging from no injection at all to 30 microliters in our system. So what can we see? We have this kind of typical MolCom problem of a high, a steep rising edge and then a slow signal decay, causing intersymbol interference if we kind of want to push symbols together, which you can see here already. So we kind of have a slow increase of the baseline. And what we can also see is, in this case with 6 different concentration levels, that our amplitude value kind of depends on how much volume we put in. So that kind of sounds great for detection. So what do we do? Now, demodulating the signal, we started off with pre-processing our data. So we get a kind of rough signal. Our sample rate isn't precisely accurate, so we have to clean it up before we go. First step is interpolation to get rid of those timing deviations, and we apply just a kind of moving averaging filter to get rid of background noise due to, for instance, environment. So with our inductance sensor, I always like to say we've got a perfect proximity sensor. You just need to wave your hand and you can see it in the detection signal. And then we split this whole section into individual symbols, and for the sake of proving our demodulation approach, we then randomly shuffled these symbols into a large training set, a validation set, and a test set. We then investigated what our detection accuracy is, both with a more conventional machine learning approach using a linear discriminant analysis and the newly developed convolutional neural network. So, linear discriminant analysis, relatively straightforward. We used 3 significant features. So we went down a whole rabbit hole of feature extraction and so on, and decided basically the rising edge, the amplitude, and the falling edge are the three dominant features that we see in our signal, and put that in a linear discriminant analysis. There's a few publications about that. I'll just call it kind of state of the art. Now, our convolutional neural network has 9 layers. So this is kind of a, let's say, default setup. Makes it simple to go, 3 convolutional layers, 3 max pooling layers, 3 fully connected layers. We use a cross entropy loss function to determine our signal loss, and add-on for optimization. In total, with this setup, training takes less than 2 minutes on a kind of normal graphics card, which you would use for deep learning approaches. So, simple setup, quick to learn, easy to work. What do we see? We have a very typical syndrome of course, luckily, most of our symbols are detected correctly. So here what you see is for 6 different symbol values, so 6 array concentration shift key, and for 8 symbols at 2 symbols per second and 4 symbols per second. So in most cases, the symbols which we detect are the ones that we expect. That's good. And in most of the other cases, we have an error by exactly 1 symbol value. So basically these neighboring layers. In total, for the low symbol rates, so of 1 symbol per second and 2 symbols per second, more than 90% of our transmitted symbols are detected absolutely correctly. And for the higher symbol rates, so for the example of 4 symbols per second at 6 different amplitude rate levels, which is like our best fit, we still get 65% completely correctly demodulated symbols. Now, applying some binary encoding and so on to use our syndrome of neighboring errors, we get a net data rate which is achievable of about 5.5 bits per second with a remaining bit error rate of 1%. Now, how does this compare to our conventional approach? So here you see some tables for 6 amplitude levels, 8 amplitude levels with the linear discriminant analysis and the convolutional neural network. Basically, if you look at the first columns, for 1 symbol per second, 2 symbols per second, they're more or less the same. So we have some deviation there, but it's not really worth mentioning. Once we go to the higher symbol rates, where inter-symbol interference gets kind of really tough, we actually see a quite significant success of the deep learning approach and better demodulation results. In conclusion, it's the first application of deep learning to some form of high modulation in molecular communication. It works. We have a better accuracy than a conventional approach. And that's the kind of major factor for me. It's much more flexible with an unknown channel. So I don't actually need an analytical model of my channel or look at feature extraction. I can get an acceptable demodulation without knowing hardly anything about my channel. In future, we'll go more down the rabbit hole of what can we do with different CNN architectures, different deep learning approaches, introduce channel memory, so use a recursive neural network, and actually investigate what actually happens when my channel is changing. So we are intending to set up a physical testbed model which has a moving channel, as we would, for instance, have inside the human body. In the stomach, when I breathe, my body moves. What actually happens in this setup when the channel changes in real time. Thank you.
Thank you, Max, for this concise and great presentation. Any questions? I think we have time, right?
We do, yeah, there's no rush.
Yeah, that's good.
You said that your input has a size of 182. Is this or 128?
128. Yeah.
Okay, yeah. Are these how many symbols are these? So
That's one symbol.
that's one symbol.
Yeah.
But wouldn't it increase your performance if you would also kind of take into account the previous symbols? So have you tried like using either like fewer samples, but or actually more samples and then include multiple symbols? Did you try that?
Not yet, but that's why I said where we want to go in the direction of recursive neural networks. So why we did that is to be fair with our conventional approach,
Okay.
where I was saying we just took those three features from one symbol isolated. It kind of felt a bit unfair to say, okay, we'll get more information in our deep learning approach. Yeah.
Could you explain the offset? I don't know if I missed that part. 'Cause in the results you're showing, you were giving there's a column of offsets. Yeah, no, back slide 8. Offset.
Yes, exactly. So yes.
So I noticed that the 4-channel in your results there was a case where there was a bigger offset than the conventional approach was actually doing better than the proposed one. So for example, offset of 1 at 4 hertz, LDA is 0.26 and then CNN is 0.15. If I'm reading that correctly.
True, yes. That is very true, yeah. So, I mean, first to explain, the offset is basically the error from our expected symbol. That's what I've been trying to show here. I didn't explain it.
Oh, like distance from the diagonal.
Yeah, yeah. So, if I transmit a 5 and detect a 4, I'm here. If I'm detecting a 3 here, detecting a 2 down here.
Okay. So the columns add up to 1.
Yeah.
I see that now.
Yeah,
Okay. So
yeah.
so you're not doing better with 0.26 being bigger than 0.15. It is you're getting that error 26% of the time versus that error 15% of the
Exactly.
time.
Yes.
Okay.
So basically, this is a list of syndromes. If you so.
Gotcha.
If you so want.
So it's really just the top row that is the overall.
Yeah.
correct
I mean, this is the interesting row.
Yeah.
And we kind of expect it to diminish down here.
Another quick question: was there any thought of hawking your 2080, or how many 2080s did you have? Your graphics card was a 2080.
Yes.
Those increased significantly in value over the previous year. I was just wondering if there was any thought of considering its market value while you were doing the testing, or was just the testing was too valuable? To
No,
give up
and
the card?
honestly, it's not mine. It's
Yeah.
rented from the colleague. So I jumped over that a bit quickly. It's not just me who did this, obviously. Jens, you all know. In between, Benjamin's one of my students, and Oliver's a colleague from information from an IT institute at Erlangen. So he actually provided the hardware equipment. So I'm afraid I
So you
won't
don't
be able
appreciate
to
you don't
make
you didn't
it.
appreciate the value of the 2080 that
No,
you were
I know.
using, is what
I know,
you're saying.
I know.
Okay.
I just could send it and it would work.
No, that's fine.
I was thinking about after it.
But it does also actually work just on my laptop. Takes a few minutes longer.
Yeah, thank you. Just, to apply these kinds of learning algorithms, then of course, you need hardware which is compatible with the application that you're using. And do you know any size, the minimum size of these processors which are able to do these kinds of algorithms, particularly this one that you have done?
Well, now we're down the lane of what Adam said, of course, the 2080 is not the smallest graphics cards you can get.
The size, I mean the volume of this, not the memory in these things. The size.
Yeah, so you mean kind of the physical size
Yes,
of the computational
yes, yeah, the
intelligence.
physical.
Yeah. So, I mean, once we've got the learn network, It's relatively compact, so I mean, then applying the train network on some form of slightly powerful microcontroller is doable. We're
Still far from the range of.
of course, yeah.
It's
But
a good, yeah. Wait, sorry.
so is that. Yes, of course. So, I mean, we're living in the world, or I'm living in the world of macroscopic molecular communication. So, kind of trying to show what we can do in principle in a testbed. Of course, that's like, you know, kilometers of what's thinkable. I could come along with Moore's law, maybe, who knows, in 20 years. Everything will be great, but there are some physical limits to that too. What I can say in that direction, also with the colleague I mentioned, Oliver, we want to go kind of down the lane of edge computing. So implement the deep learning model on an FPGA, get it as compact as we can for today's technology, which of course is still more in that dimension than in the cell dimension, obviously.
Thank you.
But in sense of, let's say, an implantable device, it's, I think, quite realistic.
Yes,
Hi, Max. Okay, my question is about an opposite use of your approach. I mean, in the case you have the symbol connected to the shape of the signal, not with the facial consideration. As an experimental point, providing a lot of data set, big data set to train is something very hard to do. I just think about if you have a simple system that you can model by a theoretical point of view, in principle you should use some signals, add some noise, and training your network with the kind of synthetic signals. Is it possible to use this kind of training to understand if the real one symbol is the correct one or not? I don't know if.
Okay, so I think a few angles to that, which I'm hearing. First aspect, yes, gigantic data. So that was 10,000 data sets we threw into training there, which takes days. Yes, I mean what you said, you could model data to then throw it into a deep learning approach, kind of would seem a bit weird because then I've already need some form of analytical model, or I suppose particle-based simulation, yes, okay, yeah. But that kind of feels a bit weird. I think what you're saying is, can I flip the whole deep learning process around? So I have a deep learning detector, can I now throw in symbols and get a signal model on the other end? Was that your question?
Yeah.
I've got no idea. I feel like saying no. Any deep learning experts here?
What about again? I think I have an idea because we're researching on that. You can use a so-called autoencoder. So that's in principle where you really go end to end. So you start from a symbol, and you really get to a detected symbol, and in between you have like an encoder network, then you have a system simulation or the real system, and then you have a decoder network. And you jointly train that so that it actually just recovers the input from the input, so to say. And that is an approach that works, and we are currently working on this. So if you're interested, I can show you some first results on that.
Okay, definitely.
Yeah.
Thank you both.
Okay, thank you very much for this. You don't have any question, right?